Communication Networks Assignment 1. So before we get into the experiment, we do need to know a few basics about personal area networks. So first of all, what is a personal area network? It's a computer network that is used for data transmission between different personal devices such as computers, telephones, digital devices, etc. And it's also used for connecting to the higher level network and internet. Personal area network can be of two types. It can be wired or wireless. A wireless personal area network, that's a WPAN, can be made using network technologies such as Bluetooth, IRDA, UWB, Z-Wave, zigbee, and body area network. However, we'll be dealing in detail with zigbee. Zigbee is typically used in low data rate applications that require long battery life and secure networking. Now, something about the history of Zigbee. Zigbee was basically conceived in 1998, standardized in 2003, and it was revised in 2006. Now, let's get into our experiment. So first, what is the objective of our assignment? So basically, we have two nodes here, node 1 and node 2. Node 1 transmits data to node 2 with no path loss. We obtain the theoretical throughput based on IEEE 802.15.4 standard, and this will be compared with the simulation result which we run using netsim. Before moving on to our simulation, we also need to understand what is CSMA and CA. It basically stands for Carrier Sense Multiple Access with Collision Avoidance. So this is basically used in computer networking. It's a network multiple access method in which carrier sensing is used, but nodes attempt to avoid collisions by transmitting only when the channel is sensed to be idle. When they do transmit, nodes transmit the packet data in its entirety. It is particularly important for wireless networks, where the collision detection of the alternative CSMA CD is unreliable due to the hidden node problem. And as we're dealing with wireless networks, this procedure becomes really important. Now, let's understand the theory behind this experiment. A packet transmission begins with a random backoff in number of slots, and here each slot is considered to be 20 TS duration, which is sampled uniformly from 0 to 2 power MACM in BE-1 and followed by a carrier collision avoidance, that is CCA. CCA failure starts a new backoff process with the backoff exponent raised by 1, that is to mac min BE plus 1, provided it is lesser than the maximum backoff value given by mac max BE. So basically all we're trying to do over here is we're trying to sense the channel, and only when the channel is free is when we send the packet. Otherwise we wait for the channel to be free and then send the packet. So a successful CCA is followed by the radio turnaround time and packet transmission. Now, if the receiver successfully receives the packet after the channel is free and the transmission has been made, without any collision or corruption due to the physical layer noise, then the receiver would send an acknowledgement after the radio turnaround time. However, a failed packet reception causes no ACK generation, that is, there wouldn't be any acknowledgement if there's a failed packet reception. The transmitter infers that the packet has failed after waiting for a certain duration called the mac-ACK wait duration, and it only retransmits the packet for a maximum of max frame retrimes and before discarding it at the MAC layer, that is, after this time it would discard it no matter what. However, we need to note that in netsim the radio turnaround time after a CCA success is not considered. So now let's actually get into our experiment wherein we simulate our given scenario using netsim. So our current scenario looks something like this. So here, as you can see, we basically have two nodes and we have a PAN controller, which is nothing but a personal area network controller. So what we're trying to do over here is transmit data from node 2 to node 3, or say node B to node C, and this is controlled or regulated by PAN controller, which is personal area network controller. So as we can see, this is how the interface of netsim looks like. We basically have grids on which we add different modules like different nodes or different data transmitters or different data receptors and different environment regulators, and give them the required settings before moving on. Now, after we give the required settings and finally start the simulation, this is how it happens. We have set the application layer payload 70 bytes in the node 1 properties, and when the packet reaches the physical layer, various other headers get added. The different headers which get added are basically as follows. There is an app layer payload which is of 70 bytes. There's a transport layer header which is of 8 bytes. There's a network layer header which is of 28 bytes. There's a MAC header which is of 5 bytes. There's a physical layer header which is of 6 bytes. Hence the total packet size would be sum of all these header files, which basically turns out to be 117 bytes. Now let's understand what actually happens in simulation. So in simulation, by default, netsim uses unslotted CSMACA, and so a packet transmission happens only after random backoff, and the carrier collision avoidance and turnaround time is followed by turnaround time and acknowledgement packet, and each of them occupies a specific set of time given by the IEEE 802.15.4 standard. And then the timing diagram over here shows exactly how this allocation is done. So as we can see, initially there's random backoff average, which takes about 3.5 slots, followed by CCA, which is 0.4 slots, followed by the turnaround time taken, which is about 0.6 slots. Now the time taken for the packet transmission from source node to destination node is given the maximum amount of time, which is 11.7 slots, as the amount of data transferred over here is 117 bytes, which we calculated previously in the last slide. Now on the destination node, again there's a certain turnaround time, which is given the time of 0.6 slots, and there is an acknowledgement which is also given the time of 0.6 slots. From IEEE standard, each slot has 20 symbols, and each symbol takes 16 microseconds for transmission. Therefore, these are how the parameters turn out to be. So as discussed and decided, the symbol time is 16 microseconds, and as we know, the slot basically consists of 20 symbols, and the slot time is 20 symbol time. That is equal to 16 microseconds into 20, which turns out to be 0.32 milliseconds. And similarly, the random backoff average, the carrier collision avoidance, the turnaround time, and the packet transmission time are basically calculated using the number of slots dedicated to them. So 3.5 into the number of slots turns out to be 1.12 millisecond, as we know that the slot time is 0.32 milliseconds. And hence similarly, we calculate time for CCA, turnaround, and packet transmission, and these turn out to be 0.128 milliseconds, 0.192 milliseconds, and 3.744 milliseconds respectively. However, we also need to add the turnaround time and acknowledgement packet time at the destination node. The above values were for the source node and for the transmission. However, now we also calculate the time at the destination node. Now at the destination node, the turnaround time turns out to be 0.6 into slots, and acknowledgement time also is the same as discussed in the timing diagram in the previous slide. So because both of these are 0.192 milliseconds, the total time is the sum of all of these, that is the time required for transmission at the source node and the time required for reception at the destination node. And the sum of all these times turns out to be 5.568 milliseconds. Now, from the definition of throughput, we know that the application throughput is nothing but 70 bytes in the app layer by 5.568 milliseconds, which turns out to be 100.574 kilobytes per second. Now what we need to remember over here is that this is a theoretical value. Okay, so now let us discuss the output which resulted from the simulation. So as we run the simulation, we got the throughput from simulation for 100 seconds to be 99.422 kilobits per second, whereas we know that the theoretical value of the throughput from the theoretical analysis which is done till now has turned out to be 100.574 kilobits per second. Now there is a difference between the throughput from simulation and the throughput from analysis. Now this obvious difference is because that the simulation time can be adjusted, and as we will see, as the simulation time keeps on increasing, our value keeps on getting closer to the throughput from analysis, which is the theoretical value. Now, using netsim, we did run simulations for different simulation times: 10 seconds, 50 seconds, 100 seconds, and 200 seconds. And as discussed in the earlier slide, our throughput did increase with increase in simulation time. As you can see, for 10, throughput is 89.712 kilobits per second. For 50, it is 98.504 kilobits per second. For 100, it is 99.422, and for 200, it is 99.994. So what we basically see is as the simulation time keeps on increasing, our throughput approaches the theoretical value. Now, in the next slide, we look at percentage changes in throughput with increase in the simulation time. Now, from a simulation time increase from 10 to 50 seconds has seen the throughput change by 9.8%, and for the next 50 seconds the change is 0.93%, and for the next 200 seconds the change is 0.57%. So what we see is that the percentage change keeps reducing as our throughput obtained from simulation keeps approaching or getting closer to the theoretical value. So now finally I'd like to conclude this experiment with follows. The slight difference in throughput is due to the fact that the average of random numbers generated for backoff need not be exactly 3.5, as the simulation is run for short time, and also in the network layer DSR protocol is running, so route setup process will take some time. And the second main important point of our conclusion is as follows: as we go on increasing the simulation time, the throughput value obtained from the simulation approaches the theoretical value, as we saw in the previous slides.